Good evening, everyone. Today's lecture, we're going to be discussing shop floor scheduling. Okay? What's the difference between shop floor scheduling and MRP? Well, the solution to an MRP problem is what? It's a schedule with weekly time buckets, right? So you'll have all your parts and you'll know how many to make each week and when to order parts and etc., right? The solution to a shop floor schedule is a Gantt chart that shows each job in its location in sequence, okay? So shop floor scheduling, think basically a Gantt chart. And so read chapters 7 and 8 in the book. They're very good. And I'm going to post some homework on lot sizing as well as scheduling. Since the book's technically out of print, I'm going to just post it, not based on the book, but make a problem similar to the book. An important point that I didn't emphasize enough last time was push versus pull. A push system is a system where all the planning is done in advance for all levels, okay? So it's based on a schedule. MRP is a push system, right? You take your forecast and then you plan to your forecast. A pull system is where items are moved from one level to the next upon request. So in the end, it's the demand that drives all the activity in a pull system. Typically, pull systems are designed to have low inventories. That's why you run a pull system. So think MRP for push, think just-in-time and Kanban for pull. Now, if you guys remember, when we talked about the Deere paper, right? It was a pull system in that customer demands something and then they can pull inventory from the supply base, right? But the number of essentially cards at the station, the number of allowable inventory was adjusted as a function of time, which would make it a hybrid of push, because you're changing the inventory levels, but actually getting the inventory is pull. Kind of an interesting paper. So, from last time, what is Kanban and Conwhip? What is Kanban and Conwhip? What does Kanban mean? Card, right? And the Kanban card specifies how many items can be in a work center. So here are finished. And here are raw. And you have the machine here. Okay? Now, if I have a Kanban of 4, that means only 4 parts can be in this system. Where can they be? Well, they could be all unfinished and the machine stops, or maybe I have 2 here, 1 here, and then 1 card is going to the prior work center to try to pull another raw material to this machine. Okay? And quite literally, think of it as a card. If I was making these projectors and doing Kanban, I put a little tag on it. And that tag would be laminated and it would follow the item. Okay? And as soon as the customer took this item, I take the Kanban and try to get another raw material to my work center to build another one. Okay? So Kanban is a way of controlling a manufacturing system that basically states you have a fixed amount of inventory at the station, or counting the call to the previous station for parts. Just in time is a management philosophy that focuses on minimizing inventory, and one of its tools is Kanban Conwhip. And we'll briefly discuss QRM as an alternative to just in time at the end of the semester. So silver meal, least unit cost, and lot for lot we talked about last time. Know how to use them to compute the production schedule. And basically, all of these algorithms try to do is solve the EOQ problem, except for now demand's not constant, but it's based on a forecast. Production planning with MRP and finite capacity scheduling softwares have been developed. And these basically take MRP and they add in setup costs, they add in capacity limits, and allow you to build a schedule. And these programs, you also need to estimate the fallout rate, the defect rate. You have to set safety stocks. In addition, they allow that. And you can set capacity limits on both production capacity and floor space. And today, many large organizations use these integrated planning programs from a variety of vendors, SAP, Oracle, and some smaller ones. Silver meal, least unit cost, or what you would call classic heuristics. You would never actually run them. And actually, you can solve the program by integer programming, so you don't even have to do them. But you have to know them for the test because there'll be a problem on one of the two. So today's topic is scheduling. Scheduling problems are everywhere. You have machine scheduling, which is what we mostly think of this in this class. You have human resources scheduling, which is a tremendous area. Think about staffing hospitals, retail, manufacturing. For instance, a hospital has to cover all the shifts, and you may need a couple hundred nurses. And you have to keep track of when the nurse wants to work, when the nurse does not want to work, etc., right? You also have to schedule the rooms in the hospital, the operating rooms, etc. And so, resource scheduling in a hospital is a big area for IEs. As a matter of fact, I got the opportunity last spring to have a talk with the IE for Texas Children's, which was kind of cool. It was interesting. They do a lot of work, a lot of projects, and it goes beyond scheduling in a hospital. They do layout and basically everything that you do in IE, you can apply to healthcare, you can apply to retail, you can apply everywhere. Another fun scheduling problem is facility scheduling. How do you coordinate the schedules of classrooms on a campus? Vehicle routing, and crew scheduling for airlines. And each problem has its own characteristic, and we're only going to talk about machine scheduling. There are multiple levels of planning in an organization, okay? And you can talk about strategic planning, where we're developing a long-range plan. And what we're really asking there is, what industries do we want to participate in? How many plants do we need? Where should we put the plants? Aggregate planning is in the medium term. How much inventory should I build? Maybe hiring and firing is either aggregate or strategic. We talked about that. MRP, how much am I going to build each week? And then finally, shop floor control. What am I going to do in the next 10 minutes at this work center? Scheduling has some vocabulary. Typically, people use I for machine and J for job. And so D sub J would just denote the due date of job J. PIJ is the processing time of job J on machine I. WJ is usually the weight of a performance metric. And then you have the completion time of a job is just when it finishes. The lateness is the completion time minus the due date. The tardiness is the maximum of 0 in the lateness. Okay? So tardiness counts late. Lateness could be negative, which would mean it would be early, right? And then finally, earliness. So each machine has some ready time. You have Java ready times. You have job arrival times. It can either be stochastic or deterministic, and the scheduling literature has a well-developed language. You can think in terms of single machine scheduling problem where you're scheduling one machine. You can think of an environment where you have parallel machines, and a parallel machine environment would be a situation where I had 3 machines, maybe printers, and I'm printing stuff off, and I could send a job to each one. Now, they could be the same or different, okay? In which case, you'd have to schedule each one of these printing presses or lathes in parallel. Now, a flow shop is where n jobs must pass through n machines. And let's not pretend that's a printer now. Let's call it a press, and then let's call this a lathe. Flow shop basically means everything goes this direction for the most part. Okay? So it flows through the system. It's not an assembly line, but parts move from the start to the finish. Finally, a job shop is a manufacturing environment where parts have different paths and move between different types of machines. So a job shop is typically, you put your lathes here, your drills here, your mills here, and I'm out of machines. Lathes, drills, mills, grinders. And you'd put lathe, lathe, mill, mill, or drill, 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 mill, mill, and a grinder. And in a job shop, the parts move in a whole bunch of different paths depending on the part being made. Okay? Now, there's basic principle that job shops tend to run high inventory. The whole idea of a job shop is you combine your machines together to get efficiencies. All the tools are in one place, right? A flow shop or a cellular system, you want the cellular, let me put that up, would be, maybe I do grinder, mill, lathe, in cell 1, and then cell 2 might be mill, drill, lathe, etc. Okay, so a part goes to a cell, is fully processed, and then leaves. Okay, and you know which way you choose your layout's important, but that's for a future lecture. What defines a machine scheduling problem? Well, first of all, you need a list of items to be scheduled, and you basically need the routing, the list of machines and alternative machines the part must visit, the processing times, the due dates. You need information that's machine specific, the ready time and the amount of time to change from job to job. And then you need an objective. And the objectives that you can have are things like make span. I got 50 jobs. What's the shortest time I can process them in? Which is the maximum of the completion time of all the jobs. You could do average flow time or weighted flow time, which is basically the sum of the flow times, the completion times. You could do the maximum lateness of a job. Each job has a due date. Take the completion time, the due date minus the completion, no, the completion time minus the due date. Find the maximum of it. Number of late jobs, another good measure, and then you can think of something else. My favorite measure in actuality is that what happens if a job's late in a facility? Anybody guess what happens if a job's late? Think of it as a fairly important job. What do? It
is kept on the priority.
Well, you can keep it on a priority, but let's say it's late. It's going to be late.
The production stops. You can't.
It will delay the...
You'll delay the customer.
Yeah.
One of the things schedulers like to do is if it's an important customer, they don't like to admit it's late. So what will they do? Well, if it was to ship LTL, they'll ship it air. Okay? And so what you often have with lateness is sort of this stepwise increasing tardiness cost, where, you know, if you miss the cutoff time for transportation, you just ship it a little faster. So you go from less than truckload to expedited ground or air freight. And as such, tardiness is often measured in days. So if the job gets done when it's supposed to get done, I'll send it on a cheap LTL carrier. If it gets done a few hours late, what's the cost? Well, I'll call the LTL carrier up. They'll pick it up late. They'll charge me $50. If it's a day or two late, I can send it expedited ground. It might cost me a couple hundred, maybe $1,000 more. And then at some point, I can't just change the mode of transportation, right? What do you have to do if you can't change the mode of transportation to get it there on time? Hint, I'm pointing to the phone, right? You call the customer and what do? It's confession time. I can't do it, right? And what's the cost of that?
Depends on the customer.
Depends on the customer and the circumstances of the customer, right? Maybe he has a ton of the part on hand and is just as happy that, you know, it's not coming in. Maybe he's short on the part and really angry, okay? So, you don't want to call the customer. It's embarrassing if nothing else. And it may be very expensive if you lose them as a customer, okay? Or, the other thing is, does your attitude when you talk to them count at that point? Yeah. I mean, this is like Operations 101. How do you make the customer happy? Well, let's say I have an order for 1,000 of these and only 200 are done. What can I do to make him happy on the phone, him or her?
Add more to the order. Add extra.
Well, you could add extra, but if 200 are already done and I'm still waiting on 800 more, what can I do?
Send the 200.
I'll send the 200 by air. You'll get them tomorrow, and you'll get the rest when they finish as quickly as possible. And we're sorry for this issue. And as long as you treat your customers fairly and keep them informed, and they usually are less mad. Doesn't mean they're not mad. Another thing that you want to keep in mind with scheduling the shop floor is you want a consistent plan. You want to avoid nervousness, where an optimization procedure selects a plan that reassigns many different machines or different start times over an alternative schedule with fewer reassignments. And so anytime you're rescheduling the shop floor, you can cause rework of supporting activities. So if people were preparing to do the job, and at the last minute you move it to a different machine, maybe the tool sets need to be reset up, etc. You can cause confusion, and it's difficult to review the schedule. And I want to put up some schedules, and this was done actually on my research for my dissertation, but I think it's a good exercise. So the first, we have the old schedule up above with those jobs, and then we add a whole bunch of new jobs. And if we let the optimization just pick whatever it wants, you can see the 3 of the 4 jobs changed machine assignments, and they're shown in red. But there's a similar schedule with the same cost where nothing changes. Here's my old schedule, and I can find a similar schedule where I keep things consistent and is cheaper. And then here's an example where there's a trade-off. Now, the point of this is if somebody sells you an optimization scheduling system, you want to be able to maintain a stable schedule in it. You don't want to constantly change your schedule around on people. So if you have to reduce, to eliminate a tardy job, or just you have to change it. But there is some benefit in both MRP and scheduling of keeping some stability on telling people what they want to do. Now, we're going to talk a little bit about dispatching rules today for constructing schedules. And so you don't even need to use optimization necessarily if you use one of these heuristics. And the simplest rule is first come, first serve. Tell your employees to work on the first job that arrives. Another rule is shortest processing time first. Tell them to work on the easiest job first. And then another rule is earliest due date. Tell them to work on the job that's due nearest in the future. And then finally, critical ratio, which is the ratio of the processing time now and when it's due. You can also look at meta-heuristics and optimal procedures. And for a lot of scheduling problems, optimal procedures can be kind of difficult to develop. So let's look at dispatching rules. Dispatching rules are how you can schedule a shop floor machine to determine what to do next. And a future schedule can be constructed based on the dispatching rules using a Gantt chart. So if I have this single machine and I have these 5 jobs and the processing times are there and the due date's there, first way I could schedule them is shortest processing time first. So job 2 has the smallest processing time, it gets to go first, job 1's next smallest, and so on. So the first job completes at time 4. Okay, schedule starts at time 0, completes at time 4. The second job starts at time 4 and you add 6 to it, so you complete at time 10. The third job starts at time 10, you add 7 to it, you complete at time 17, and so on. Then you compare the due date to the completion time, and we find that one job is tardy. Okay? And it's 21 units late. And this is based on shortest processing time first. If we did it in terms of due dates and sorted the jobs based on their due date, we would find that no jobs are late, but the average completion time goes from 18.6 to 21.4. And there's a classic rule, actually a proof, that says EDD, earliest due date first, minimizes maximum lateness for a single machine schedule. And this is kind of cool. A lot of times working on due date's a great job, a great way of running a facility, as long as there aren't significant setup times that are sequence dependent. Number of tardy jobs can be minimized by Moore's algorithm. And basically, you sort it by due date, and the first job late, you eliminate the longest processing job and continue to sort by due date. And I'm not going to ask that on the test, but earliest due date is great, but critical ratio might perform better considering processing times. And basically, you just take the due date minus the current time divided by the processing time, and it kind of combines earliest due date with shortest processing time first. Sequence-dependent setups are common in many industries: printing, batch chemical, discrete part. And basically all this means is if the time between operations is different based on the prior operation, the setup time is sequence-dependent. And you typically have a setup changeover matrix that tells you the time between changing between different types of jobs. If the setup time is the same regardless, then it's sequence-independent. And a good example of this would be the printing industry, where you have paper size, okay? If you change the paper size, you have to change all the rollers out in the machine. Might take you a couple of hours, right? Whereas if the next job had the same paper size, same colors, no time at all. And if you had to change the colors off, it might take maybe 20 minutes, okay? Everybody gets sequence dependent, right? So if you have a situation with sequence dependent, there's a dispatching rule here. Apparent tardiness costs with setups to rank the jobs. And the rule ranks the jobs that can be started based on the equation that follows, where J is the job and L is the prior job. And basically it has three terms. The wait term says do the job with the most importance first. Dividing by the processing time says do the shortest job first. This next term is based on the due date and basically tells me do jobs that are due in the near future first, and the final term is based on the setup time. And I'm not going to make you use that dispatching rule on the test. So the objectives of scheduling from the book is to minimize work in process, minimize average flow time, maintain high worker and machine utilization, provide status on jobs, minimize setup time, minimize production cost. And often these objectives conflict. So I'm going to pause for a second and then continue with Part B in a moment.